Welcome children. After going through various procedures that we have learnt in differentiation, different functions we have come across and we learnt how to differentiate them. Now we can discuss the applications of derivatives. One of the most important applications among derivatives, that is about increasing and decreasing functions. Now, before dealing with increasing and decreasing functions, we should first understand what is meant by functions which are increasing or which are decreasing. Let us take an example to understand it better. Look at this curve. You can see as the value of x increases from left to right, if we assume this curve as y is equal to fx, then you will find with a change in x there is a change in y also. In few stretches, as x is increasing means its value is moving from left to right, or we can say as the value of x increases from left to right when we are moving, you will see in some of the stretch the y corresponding to it falls. In some of the stretches y corresponding to it goes higher and higher. So let us try to locate such stretches first. You can see here on moving from left to right, you can see x is increasing but the curve is coming down. Okay, it keeps on coming down till till x becomes -1. And after that, as x further increases, you will find corresponding to it y is also increasing. You can see the curve going higher. And the moment x becomes 1, after that also we see that the curve is going down. So that means what? The values of y are falling. So what do we see? When x is increasing, as we move from left to right, if y falls, that means, or if the values of y are decreasing, or we can say the value of fx is decreasing, that means the function is decreasing. See here, x was increasing, but corresponding to it, fx was decreasing. So we could see that the curve is coming down. Now in this stretch from -1 to 1, x is increasing and fx is also increasing. And fx is increasing, that means the curve is also increasing. So we see a relation between x and y here, which helps us in making out that for these particular intervals, when x is belonging to those particular intervals, the curve may be increasing or decreasing. So as per this curve, if you see, you can find for all x belonging to this interval -infinity to -1. As x was moving from -infinity to -1, what happened? The curve was coming down. And same nature we observed when x was moving in the interval 1 to infinity. So if we take these two intervals, in both these intervals we could see though x was increasing but y corresponding to it was decreasing. So in these intervals, fx, the function is decreasing. Okay, that is what we saw according to the curve. Whereas for all x belonging to -1 to 1 within this interval, we could see the curve is increasing. Y was increasing and the curve was increasing. Now let us try to state this condition. The definition says if I is an open interval which is contained in the domain of real valued function. So we are talking about an interval which is subset of the real numbers, that is -infinity to infinity. Then f is said to be increasing on this interval if x1 less than x2. That means if there are two values for x, one is x, another is x2, such that x1 is smaller than x2. So these numbers are belonging to the given interval where x1 is smaller than x2. If we see corresponding to this, fx1 is also less than equal to fx2. So you can see the image of x1 will be fx1, the image of x2 will be fx2. So if we notice for all x1 strictly less than x2, if fx1 comes out to be less than equal to fx2, then the function is termed as increasing. This is an example of increasing function. If you look at this curve, okay, and let us go through this also, then we'll find what is the difference between these two statements. The next one says it is strictly increasing on I if for x1 less than x2 in this interval, fx1 is strictly less than fx2. Okay, now let us understand these two cases. Look at the second figure. It is of strictly increasing function. This is increasing function. So what difference do you observe between these two? You will find there is a stretch in this curve where corresponding to different values of x1, maybe their images are same. So if you look at this part, if I say x1 is this point is having x coordinate x1, then its y coordinate will be fx1. Okay, and if I assume this point has got x coordinate x2, then its y coordinate will be fx2. So over here what do we see? X1 is smaller than x2, but fx1 is equal to fx2. So only in this stretch. In rest of the stretches you will find for x1 less than x2, fx1 is also less than fx2. So if you meet such condition that there are few values for x1 and x2 for which their images can be equal also, then we say the function is increasing. We don't say it is strictly increasing. Okay, it will be termed as strictly increasing if for every x1 less than x2, fx1 is also strictly less than fx2. Okay, then the function is strictly increasing. Now same holds for decreasing function or strictly decreasing function. It says if x1 is less than x2 but fx1 is coming greater than equal to fx2. So this shows what? X1 is increasing from as we move from left to right, but their images, okay, they are falling down. For x1, fx1 was a larger value, and for x2 the image was fx2, that is coming out to be a smaller value. Look at this stretch of curve. As we move from left to right, x1 is increasing, but look at fx, it is decreasing. Within this interval, x1 and x2 are two different numbers, but fx2 remains same. Here again, what happens? Here fx1 and fx2 remain same, but in this case again, x1 is less than x2 as we are moving from left to right, but fx1 is coming greater than fx2. So this is an example of decreasing function. Over here, it is strictness, strictly decreasing. We don't have any two different values of x for which fx comes out to be same. So that is the difference between strictly increasing or increasing function or decreasing and strictly decreasing function. Then look at the last case here. We are calling this as neither an increasing or decreasing function. The reason being, if we don't define the interval, in which interval you are checking the nature of the function. If that is not defined as a whole, if I say on this real line, or let us say from this point to this point, if I extend it, say this point is A and this is B. If this is the interval you are taking, then in this entire interval, the behavior keeps on changing. It is increasing, then decreasing, then again increasing. So it is not following the same behavior. So if you come across such condition, then within that interval, we cannot call it increasing or decreasing function. We say it is neither increasing nor decreasing. If you look at only this part, from A to 0, okay, in this part we can say it is strictly increasing, but as a whole in the interval a to b, we will say it is neither increasing nor decreasing. Now this we understood the concept of increasing and decreasing function using the nature of x and the nature of y corresponding to it. Let us see how it can be explained using derivatives. So we come to the theorem which states if f is a function which is continuous in this closed interval and it is differentiable on this open interval. Then f is increasing in this closed interval if f dash x is greater than 0. Now this is what you need to understand. What is meant by f dash x greater than 0? Okay, f dash x means derivative of fx. Now look at this curve. If you see this interval from a to b, now from within this curve, there are infinite points. At each point, you try to make a tangent. Wherever you want to draw, you can draw one tangent here. You can take this point, wherever you will take. You can see this is one tangent drawn here. If I just extend it and let it meet the x-axis and say it is inclined at an angle theta 1 here. So can you check what will be the nature of slope of this tangent? You can see slope of the tangent will be tan theta 1. Okay, this is slope of tangent. And what is it? Can we call it positive? See, theta 1 is an acute angle. So tan of an acute angle is positive. That is greater than 0. This is greater than 0 as theta 1 is acute. Okay, now see, if tan theta 1 is slope of tangent, then what is f dash x? How do we define a derivative? Derivative is nothing but slope of the tangent at that particular point. So slope of tangent is also f dash x. So that means what we have shown? We have shown f dash x is greater than 0. So if you see that in a particular interval, the derivative of the function is coming strictly greater than 0, you can say the function is increasing. Look at this curve. Within this interval a to b, the function is increasing. As we move from left to right, y keeps on increasing. As x is increasing, y is also increasing. And at any point you draw the tangent, you will see it will make an acute angle with the x-axis. So its slope will be always positive. So this is how we can use derivatives to make out whether the function is increasing or not. Now look at the second curve. You can easily see the curve is coming down. As x is increasing, y is decreasing. So at these infinite points, you pick up any point and draw a tangent at that point. You will see that tangent is inclined at an obtuse angle with the x-axis. So you can see in this second case, f dash x, which happens to be slope of the tangent, and according to this diagram, the slope of the tangent will be tan theta 2. And we can easily see it will be negative. The reason being theta 2 is obtuse. So what is the nature of angle theta 2? It is 90 plus angle. It falls in the second quadrant. And in the second quadrant, tan is negative. So you can understand this definition better, and you can understand how derivatives can be used to find the nature of the function. So we can go through it once more. So we can say if the given function will be increasing in the closed interval if its derivative is strictly greater than 0 in this open interval. Okay. In the same way, it will be decreasing in the closed interval a to b if its derivative is strictly less than 0 for each x belonging to the open interval AB. Now then there is a third case. If it comes out to be 0. Now f dash x becoming 0 means slope of the tangent is 0. That means the tangent is parallel to the x-axis. Okay, so that means you are making the tangent at a point where the function is becoming constant. So that will be termed as a constant function. If for various values of x, as you can see, if we take the open interval AB, if in this entire interval the derivative at each point is coming out to be 0, that means it is a constant function. Then only we can get the derivative at those points equal to 0. Because the tangents at those points, at each point, because it is a constant function, the tangent will obviously come out to be parallel to the x-axis. In fact, the function itself will be a function which will, if you draw its curve, it will be parallel to the x-axis.